Alright, so this presentation is about physics and everything you need to know about physics for your IDC and IE, hopefully. Let's first have a look at a few relationships, alright, with regards to pressure, volume, density. So at the surface, you have one bar of pressure. That bar of pressure comes from the atmosphere. So if this is our world, this is the atmosphere, so up here is space, alright, down here is Australia. The weight of the air that is there exerts one bar of pressure at the surface. Let's just assume we have at the surface a volume of 1 liter for our calculations, alright? And also at the surface, the density is going to be ×1, and the gauge pressure is 0. So the gauge pressure is your depth gauge, alright? Obviously, it does not count that first bar of pressure, because otherwise it wouldn't say 0 at the surface. As we descend, there is more pressure, the gauge goes up because of that pressure. So obviously because of that, at the surface, it is 0. So gauge pressure does not take into account atmospheric pressure. So if we go to 10 meters, right, we have 2 bar of pressure, right, and that is accurate for salt water. Right. The weight of that water column is exerting pressure, right, and we have 2 bar. Now, our balloon that had 1 liter of volume, taking it down to 10 meters, right, is all of a sudden going to be halved. Right. So 2 bar of pressure exert will have the effect that that volume decreases by half. Basically, the way you would calculate that is you would divide 1 by 2, which gives you half a liter.
It'd be crazy out there, you know.
Right. The density.
With any boat operating, you know, it's dropping like flies. The numbers. You'd be lucky to have 100 people on a big boat by the time to leave. And like 200 people cancelled today.
The density all of a sudden is twice as much. Alright, so the density all of a sudden is twice as much because you have twice the pressure. Alright, the volume is half, that means that that air is only taking up half the space as it was normally, and therefore it must be twice as dense. And the gauge pressure, well, the gauge pressure now says 1 atmosphere or 1 bar at 10 meters because it doesn't take into account that atmospheric pressure. And that goes down like that in increments, right? 1, 2, 3, 4 bar, 1 liter, half a liter, third of a liter, quarter of a liter, fifth of a liter. All right, 1, 2, 3, 4, 5 times the density, all right, and gauge pressure. You have that. Make sense? Yep. All right. Notice that the biggest volume change. The biggest volume change is in the first 10 meters, right? From here to here, from 1 liter to half a liter, the difference there is 0.5 of a liter. Now, if we go 10 meters deeper to 20 meters, where we have a third of a liter of the volume, the change here is only 0.17 liters. So when you have students, right, and they may be slow at equalizing, right, the first few meters to descend is where the biggest volume change is, or where we have to equalize so much more. So if somebody can equalize to 3 or 4 meters, right, as they're going deeper, it actually gets easier for them. Make sense? Next thing we're going to have a look at is what effect we have when it comes to physics. A couple of things to remember. If something is going to get greater, you must multiply. Therefore, if something is going to get smaller, you must divide. Alright, let's have a look at this. If we're breathing 1.5% carbon monoxide at the surface, so we have a tank and it's contaminated, carbon monoxide is in there, and it has 1.5% carbon monoxide at the surface in it. What is the effect breathing this gas at 40 meters? What's the equivalent of it? Alright. Really easy way to figure these things out is have a think about it. Is it going to get greater? I must multiply. Is it going to get smaller? I must divide. We know that going down the air is going to be more dense. Alright? So therefore with every breath that I take more air in than I would at the surface. So therefore the effect is going to become greater. Make sense? What do we know? We know that the density at 5 meters is 5 times what it is at the surface. And therefore, you are breathing in 5 times as much air as you would be at the surface. Therefore, we must multiply 1.5% carbon monoxide, I know that, times 5 times the amount of air that I'm breathing in at 40 meters is 7.5. So a 1.5% contamination of air at the surface is equivalent to a 7.5% contamination if I was to take that same gas and breathe it at 40 meters. Makes sense? Few constants. These things you just need to remember. Alright? Heat. Water conducts heat 20 times better than air. Alright? You know what? Density. Yeah. Color. Red is the first color that gets absorbed. Right? You always see photographers, what do they have in front of their camera? A red filter. Okay. Sound. Sound travels 4 times faster than what it does in air because, again, it is denser than air. Water is denser than air. Okay? So it travels faster through that medium. And that is one of the reasons why we don't really know where the sound comes from. It sounds as if it comes from above. Right, here on land, sound hits this ear, then this ear. And that is just enough time for us to figure out which direction that sound is coming from. However, in underwater, where that sound is 4 times faster, the time difference between ear and ear is so small that we can't figure out where it's coming from. So we think about it's coming from all over the place. Another constant, fresh water, 1 liter is 1 kilogram. Salt water is heavier. Just think about it this way, it has salt in it, right? Therefore it's heavier. Right? And it weighs 1.03 kilos. When it comes to vision, objects appear a quarter closer and a third larger underwater. Right? So everything is closer and larger. And you see that quite often, especially with new students. If they want to turn around 180 degrees or 360 degrees, they usually stop about here instead of turning all the way. Because as their brain is concerned, they have turned around, right? Because everything looks closer and larger. There is, however, something called visual reversal. Visual reversal, think of it, it's the other way around. Right? And that happens, objects appear further away than what they actually are. And that happens when the water is really turbid. Right? Water turbidity is the contributing factor there. For our purposes, air is made up of 21% oxygen and 79% nitrogen. There are some other stuff in there, but for us, for scuba diving, that is what we consider it to be. Alright, let's have a look at pressure. Alright, so we know that 1 liter of salt water is 1.03 kilograms, and therefore 10 meters equals 1 bar of pressure. Alright, we also know that 1 liter of fresh water equals 1 kilogram, and every 10 meters it exerts 0.97 bar of pressure. That is the only place where I've ever encountered that the metric system doesn't quite add up. You know, like metric system should be if 1 liter equals 1 kilogram, then for 10 meters down we should have 1 bar of pressure. You know, because everything is so constant in the metric system, except here. So salt water, 1 liter is 1.03 kilos, and every 10 meters exerts 1 bar of pressure. But 1 liter of fresh water is only 1 kilogram and only exerts 0.97 bar of pressure. So if this is pressure here, all right, salt water exerts 1 bar every 10 meters, and fresh water only 0.97. Let's have a look at these relationships here. We have depth of 0 meters, so therefore the gauge pressure is going to be 0 because it doesn't take the atmospheric pressure into account. All right. At 10 meters, I have 1 bar gauge pressure, all right. And that liter of salt water is going to weigh 1.03 kilograms. All right. Obviously, the weight of the salt water stays the same. The deeper I go, the more pressure there is. All right. So let's have a look of how we work out what the equivalent is in fresh water. Well, the equivalent in fresh water, 1 bar divided by 1.03, the weight of that salt water, gives me 0.97 bar. So in fresh water, the 10 meters that I descend only is 0.97 bar. Okay, and that would be the gauge pressure. Right? If I was looking for absolute pressure in fresh water at 10 meters, it would be 1.97. Okay. So at 2 bar, at 20 meters, I have 2 bar pressure, divided by 1.03, and that will give me 1.94. Again, if I was to look at what is the absolute pressure here, I would have to add 1 bar for the atmospheric pressure to the gauge pressure in order to work that out. So there we have 2.94. At 30 meters. And this example here, just to show how it works, is 34 meters. All right. So at 34 meters, I would have 3.4 bar of pressure. Divide that by 1.03, and so therefore at 34 meters, I would have 3.3 bar of gauge pressure equivalent in fresh water. We just discussed absolute pressure. All right, so let's have a look again. Depth, gauge pressure in salt water, atmospheric pressure, obviously I always have 1 bar of atmospheric pressure, absolute pressure in salt water versus absolute pressure in fresh water. Right. This is straightforward. 10 meters, 1 bar, 1 atmospheric pressure, add the 2 together, I have 2 bar of absolute pressure. But what is the absolute pressure in fresh water? Well, just like I did the calculation before, I need to divide 1 by 1.03 gives me 0.97. I add the 1 atmosphere of atmospheric pressure, gives me an absolute pressure of 1.97. And I just repeat the same calculations, just replace the difference as far as pressure is concerned to work out those calculations. With the 34 meters, again, I've got 3.4 bar of pressure. Divide that by 1.03, it's 3.3 plus 1 bar of atmospheric pressure is 4.3. Okay. All right, let's have a look at displacement. All right, Archimedes' principle. All right, that eureka moment. All right, let's have a look at that for 1 second.
There's no such thing as a perfect writer. This is why I use regularly to check them.
If I put a comma.
history and have led to some truly amazing discoveries. Take this story, for example. There once was a fellow named Archimedes, who was born in 287 BC in the city of Syracuse in Sicily. He was a Greek mathematician, physicist, engineer, inventor, and astronomer. One day, Archimedes was summoned by the king of Sicily to investigate if he had been cheated by a goldsmith. The king said he had given a goldsmith the exact amount of gold needed to make a crown. However, when the crown was ready, the king suspected that the goldsmith cheated and slipped some silver into the crown, keeping some of the gold for himself. The king asked Archimedes to solve the problem, but there was a catch. He couldn't do any damage to the crown. One day, while taking his bath, Archimedes noticed that the water level in the bathtub rose and overflowed as he immersed himself into the tub. He suddenly realized that how much water was displaced depended on how much of his body was immersed. This discovery excited him so much that he jumped out of the tub and ran through the streets naked, shouting, "Eureka!" which comes from the ancient Greek name, "I found it." What did he find? Well, he found a way to solve the key's problem. You see, Archimedes needed to check the crown's density to see if it was the same as the density of pure gold. Density is a measure of an object's mass divided by its volume. Pure gold is very dense, while silver is less dense. So if there was silver in the crown, it would be less dense than if it were made of pure gold. And no matter what it was made of, the crown would be the same shape, which means the same volume. So if Archimedes could measure the mass of the crown first and then measure its volume, he could find out how dense it was. But it is not easy to measure a crown's volume. It has an irregular shape that's different from a simple box or ball. You can't measure its size and multiply it like you might for other shapes. The solution, Archimedes realized, was to give the crown a bath. By placing it in water and seeing how much water was displaced, you could measure the volume, and you calculate the density of the crown. If the crown was less dense than pure gold, then the goldsmith most definitely cheated the king. When Archimedes went back to the king and did his test, the story says, he found that the goldsmith had indeed cheated the king and slipped some silver in. These days, using the way an object displaces water to measure volume is called Archimedes' principle. The next time you take a bath, you can see Archimedes' principle in action. And maybe you'll have a genius idea of your own.
So, Archimedes, he figured out, for example, why a boat floats and a small piece of weight sinks to the bottom. Alright? So if I have an object that weighs 5 kilos, it is always going to be weighing 5 kilos. Right? Just because I put it in water doesn't mean it no longer weighs 5 kilos, it still weighs 5 kilos. But when I put it in water, in this full tub here, that volume overflows. And the weight of that water, right, actually gives it an up force, if you want to call it that. It's going to make that lighter. You've noticed yourself that when you go scuba diving, you put your gear on, it's very heavy on land, and once you're in the water, you can't hardly feel it. You may have picked up a person in a swimming pool, like this. You can carry them around all day. However, as soon as you step out of the water, they become heavy again. Alright? So, we have a down force and an up force. And the up force is equal of the amount of water it displaces. Right? The weight of the water that it displaces, that's the important thing. It's equal to the weight of the water that it displaces, not how many liters it displaces. The weight of that water. Why is that important? Because salt water weighs more than fresh water. Right? This object will displace the same amount of liter, whether it's in fresh water or in salt water, but that water weighs different amounts. So in this case here, right, it weighs 5 kilos, gets buoyed up by 2 kilos, so all of a sudden the weight of that object underwater is only 3 kilos. Well, the weight itself is still 5 kilos, but you can lift it by only using 3 kilos. So, that's the same reason why a boat floats, right? And for example, a weight on our weight belt sinks, even though the boat is so much heavier, right? The amount of water that is displaced by the boat, right, is more than the boat itself weighs, so it forces it up. Whereas the weight of the water that our weight belt displaces is less, and and that's why that sinks. Alright, let's have a look at an example. An object weighs 55 kilo and is neutrally buoyant in salt water. What is the volume it displaces? Okay, so we're in salt water. That's important, we need to remember that we're in salt water. And what I would suggest is to make notes like this when you're doing your exams so you don't forget. Salt water, 1.03 kilos. Alright, we know the constant volume is measured in liters and 1 liter of salt water weighs 1.03 kilos. Would it display more or less than 55 liters? Well, the answer is less. Why? How do we get there? If something is less, then we need to divide. 55 kilos divided by 1.03 kilos, every kilo of salt water, or every liter of salt water, is 53.4 liters of volume displaced. So it displaces 53.4 liters, which is the equivalent of 55 kilos, and that makes it neutrally buoyant. If we place this object in fresh water, would it sink or would it float? It would sink. It would sink. Why? Because objects are more buoyant in salt water than what they are in fresh water, because salt water is heavier. Let's have a look at density. Alright. How many liters of air do we have to pump from the surface to a 60 liter container, which is at 30 meters? So if I have this bucket here, and I used to work in that, and let's say for argument's sake that that bucket has an internal volume of 60 liters. Obviously it's got much more, but let's just assume for this example that the internal volume of that is 60 liters. So how many liters of air do I have to pump from the surface to a 60 liter container, which is at 30 meters? So I'm pumping from the top down to the bottom at 30 meters. What do I know? What happens to air when we descend? The air becomes denser, so it uses up less space. At 30 meters, the density is 4 times as what is at the surface. So would it be more or less than 60 liters? Well, because of the fact that it's denser, it's going to be obviously more. Therefore, I have to multiply 60 liters times 4 times the density is 240 liters. So in order to fill that 60 liter container up at 30 meters, I actually need to pump 240 liters down to the bottom. Alright, this is me when I was doing my solo diver course. Alright, I had a tank there which I needed to breathe empty to find out how much air I would consume at the surface. So if it takes me 60 minutes to breathe this tank empty, how long would that same tank last me at 20 meters? Again, this is a density question because at 20 meters that air is going to be denser, smaller. I'm going to breathe in more than what I would at the surface. So we know that as we descend, the air becomes denser. The density at 20 meters is 3 times as much. Is the air going to last me longer or less? It's going to last me less. I already know that without doing any calculations. So therefore I need to divide. So therefore 60 minutes divided by 3 times the density. This tank is only going to last me 20 minutes at 20 meters depth. Make sense? Alright, let's have a look at density and volume. A sealed flexible container has a volume of 2 liters at 30 meters. What will its volume be at the surface? So I have the balloon and I am at 30 meters and it's got 2 liters of volume. Right? What happens when I bring it to the surface? What happens to air as we ascend? Well, simple, it expands. Right? As we're going up, the air is going to expand and get bigger, so the volume increases. If something becomes greater, what do we need to do? We need to multiply. The density at 30 meters we know is 4. So therefore, the 2-liter balloon is going to have to be multiplied by 4. So at the surface, it has an equivalent volume of 8 liters. Right. So it's really, really simple. If something is going to get greater, multiply. If something is going to get smaller, divide. Alright. So let's have a look here. I have a sealed flexible container. I have a table here with depth, and I have the density over here, which we've got over already. Very straightforward. I have my balloon, which has a volume of 2 liters at 30 meters. Alright. And now I'm going to bring this balloon up to the surface, where it becomes bigger to 8 liters. 2 times 4. Yeah. 2 times 4 is 8. Alright, let's make things a little bit more complicated. A sealed flexible container has a volume of 2 liters at 30 meters. What will its volume be at 20 meters? So what I need to do here, in order to work this out, I need to bring the balloon up to the surface, and then I need to bring him back down again. So we've already done that with this balloon. Bring the object to the surface first. 2 liters times 4 is 8 liters. And then take it back to 20 meters, where it's going to get smaller again, so this time I divide. 8 liters divided by 3, which is the density at 20 meters, is 2.67. If I look here, 2 liters at 30 meters, bring out to the surface is 8 liters, and then bring it back down to 20 meters is 2.67 meters. Remember, just a short while ago, I said the biggest volume change happens obviously in the first 10 meters, or even in the first 5 meters, or the first meter, whichever you want to look at it. Right? And this is a real good example, because have a look here. The difference in volume from 30 to 20 meters is only 0.67. Right? But the shallower I go, the more the volume change happens. So from an equalizing point of view, right, again, I must equalize more in the first 10 meters than I must in the next 10 meters, right, and it gets easier and easier. Let's have another look at density and volume. If a bucket is filled to 25% of its capacity at 30 meters, to what capacity will it be filled at the surface and at 10 meters? So 2 questions there. Alright, so this bucket, this black area here is air. It's 25% full at 30 meters. Well, if we bring the object to the surface first, will it be larger or smaller? We know it's going to be larger. If something's going to get bigger, I need to multiply. 25% capacity times 4, that's the density at 30 meters, is going to be 100% full. So bringing that bucket back to the surface is going to be completely full. Then take it back to 10 meters. We know it's going to be smaller, therefore I need to multiply. Divide. Smaller, divide. And my 100% capacity at 10 meters, we have 2 times the density is 50% capacity. So all of a sudden, that is only half full. Does that make sense? Let's have a look at displacement. A 500 kilogram cement block in 19 meters of fresh water displaces 300 liters. How much water must be displaced to move the block? Alright. What do we know? We know that we have a downforce of 500 kilos. That cement block weighs 500 kilos. Doesn't matter if it's in water or not, it weighs 500 kilos. So it has a downforce of 500 kilos. We are in fresh water, which is very important. Are we in fresh water or salt water? Alright, 1 liter equals 1 kilo. It displaces 300 liters. Because it displaces 300 liters, alright, it is also going to have an upforce of 300 kilos. For every liter that it displaces, that is 1 kilogram, 300 liters times 1 is 300 kilos of up force. So the way I can simply look at that is I have 500 kilos pushing down, 300 kilos pushing up. All of a sudden, that block can be lifted by just lifting up 200 kilos. Even though it weighs 500, because I've got that up force of 300, right? Making it lighter than what it actually is. Does the depth matter? It has nothing to do with pressure. Right? It has absolutely nothing to do with pressure. Okay? The question asks for the amount of water that it requires displacing. Does fresh or salt water make a difference? Absolutely. Okay? Salt water weighs 1.03 kilos. Right? So that water that it's displacing is going to weigh more. So let's have a look. Same question, only this time it's salt water. We know we've got 500 kilos pushing down. We know that salt water is 1.03 kilos. We know that 300 liters displacement equals 300 liters times 1.03, because every liter of salt water is 1.03 kilos. So therefore 309 kilos of up force this time. Right. Same as before, 500 kilos pushing down, 309 pushing up. So all of a sudden I only need 191 kilos, not water, kilos of up force. Every liter of salt water is 1.03. So I would need to divide 191 kilos by 1.03 to give me 185.44 liters. So if I wanted to know how much volume needs to be displaced with a lift bag, alright, it would need to be 185.44 liters, because that weighs 191 kilos. Okay. Alright, let's have a look at volume and pressure. Oh, look at that good looking guy. Alright, if I have a scuba tank, such as these ones here, and I leave them in the sun, and they're going to heat up, what do you think is going to happen to the pressure? It's going to increase. Alright? They heat up, the pressure increases. If I take the balloon and leave that balloon lying in the sun, and it heats up, because it's not an inflexible container, it is a flexible container, it will expand and the volume will get bigger. So what happens in the scuba tank? The air becomes hot, the molecules inside get excited, they bounce all around, but they can't go anywhere because the tank is sturdy. So therefore the pressure increases because they're bouncing against the walls. But in the balloon, they're bouncing against the balloon, and the balloon actually will stretch, and so therefore the volume increases. Let's have a look at partial pressure. A guy called Dalton, alright, he found out that the total pressure of a mixed gas is equal to the sum of the partial pressure of the individual gases. What does that mean? Well, let's put it into perspective with air. We have 21% oxygen and 79% nitrogen in air. Right? The pressure that the oxygen is exerting is called partial pressure. The pressure that the nitrogen is exerting is also called partial pressure. If I add those two together, I don't have partial pressure anymore. I now have total pressure. So total pressure equals the sum of the two partial pressures. Let's look at that in a bit more detail. Right? Here I have my depth. Here I have my pressure. Oxygen, nitrogen. 21% and 79%. At the surface, where I have 1 bar of pressure, 21% oxygen is exerting 0.21 bar of pressure. It's 21% of 1 bar. And the nitrogen is exerting 0.79 bar of pressure. It's 79% of 1 bar. The two added together is 100% or 1 bar. At 10 meters, 21% of 2 bar is 0.42 bar, and 79% of 2 bar is 1.58 bar. Add these two together, you have 2 bar. But this is the partial pressure of oxygen, this is the partial pressure of nitrogen. And simply going down, so on and so forth like that. Interesting to note here that at 40 meters, where we have 5 bar pressure, we have 21% oxygen, 21% of 5 bar is 1.05. So that's almost the equivalent as breathing in 100% pure oxygen. Okay. A balloon filled with air is taken to 20 meters. What partial pressure of nitrogen? Well, we know pressure at 20 meters is 3 bar. Air is 21% oxygen and 79% nitrogen. 79% of the pressure is exerted by the nitrogen. So therefore, 3 bar divided by 79% is 2.37 bar of partial pressure of nitrogen. Saturation and supersaturation. Supersaturation is a state of a solution that contains more of the dissolved gas than could be dissolved by the solvent under normal circumstances. Ooh, what does that mean? Alright. If I go diving, my body absorbs nitrogen. Alright. When I come back up, I am supersaturated. I have more nitrogen in my body than I would normally have here at the surface. At the surface, I'm saturated. My body is no longer absorbing any more nitrogen. When I go down, my body absorbs nitrogen. I come back up. I'm now supersaturated. My body releases nitrogen until that equivalent or equilibrium of saturation is achieved. If I go to altitude, up on a mountain, I am here saturated, but because there's less pressure at altitude, I have more nitrogen in my body than I would if I was up there. My body is eliminating that nitrogen. I am supersaturated at altitude until such a point where that nitrogen dissolves out of my body to become saturated again. Okay. At the surface, we are saturated. We're not absorbing anymore. At depth, we absorb more. Come back to the surface, we are supersaturated and hold more nitrogen than in the saturated state before the dive. And that is pretty much what you need to know about physics.